In the previous video, we saw that the void loop function takes some time to run each time, and that time taken by the void loop to run once is nothing but your sampling interval, because you take sample at the first line every time using the analog read function, and the time interval between two consecutive analog reads is nothing but your sampling interval. We discussed about two cases earlier which are of less trouble. However, there is a troublesome case which will arise when your loop runtime is greater than your switching period, which in this case is 50 microseconds. When I say that my loop runtime is greater than 50 microseconds, I simply mean to say that my sampling interval is greater than my switching period. The best practice is to have the sampling interval equal to the switching period. It may even be lesser than the switching period if you are taking 2 samples per switching cycle. However, here it is greater than the switching period. So this pushes us to a position where we have to first analyze whether this is fine or not. If you remember this from the second video, I believe, of this entire Arduino series, we might have come across a system like this in which we will face our transfer function here, which is our del v of top s by del d of s transfer function, and then since we are using an integral controller, we will have a ki by s here. So the loop gain under such a scenario is nothing but the product of this block and this block, which is this. So this is a transfer function of the buck converter, that is output to control variable transfer function, multiplied by the transfer function of the controller. However, if this effect is now being present, that is, this is no longer a continuous time domain system, I am trying to model this delay, that is, this entire time taken for computing the loop once. I am taking that entire time into account in my control system, and I am modeling it as a delay block. So this and this are same, except that in the feedback loop there is a delay. First question, why am I modeling this as e power minus s td? Here td is nothing but your loop runtime, or otherwise called as your loop delay. I am referring this as loop delay here. Next, why is this not some other thing? Why not sin td? Why not cos td? Something. Why is it e power minus s td? This is because it is derived from shifting property of Laplace transform, time shifting property. So I do not wish to spend more time here. So this is basically derived from time shifting property. So now your loop gain is this transfer function multiplied by this transfer function multiplied by this delay, the modeled delay what we have put. So now when you further expand this here, this e power minus x can be expanded as 1 minus x by 1 factorial plus x square by 2 factorial minus x cube by 3 factorial plus so on. Here our x is nothing but s into td, and when I am expanding e power minus std in this format, std by 1 factorial plus, the moment I say std the whole square by 2 factorial, already my delay time, which I computed earlier, that is the delay time here, is actually 100 microsecond. Instead of being 50 microsecond, it is 100 microsecond. So my loop runtime is 100 microsecond. I have already shown how to measure this loop time, the time taken to run this loop once in the previous video. It is almost at the end of the previous video. If you have not watched it, please watch it. So here our loop runtime is 100 microsecond. Therefore, this TD here, that is my loop runtime, is 100 microsecond. So when I put 100 microsecond here, my TD is now 0. Maybe 3 zeros, the whole square. This will be my TD now, S into TD. So S square into TD square will be this much. So this is a infinitesimally small number. So you can neglect all the higher order terms. Therefore, your e power minus std will be simply equal to only these first two terms. 1 divided by 1 factorial is nothing but 1. That is the reason why we are writing e power minus std as something like this. So when I'm substituting all the values, my loop gain will be this transfer function, which is del v naught of s by del d of transfer function, which is written here, multiplied by k by s, whatever k you have already got in the second video, by the procedure of the second video by auto tuning. That value multiplied by 1 minus s into td. This 0.0001 is 100 microseconds in seconds, and this s is for Laplace transform. So this will be your loop gain. So you are simplifying this and obtaining a simplified loop gain. Now this is nothing but your loop gain of this system, including your loop delay. Now I want to analyze this transfer function. I want to see whether this transfer function is fine or not, whether my system is stable or not. For that, I am going to MATLAB. You can do this stability analysis in multiple ways. I am simply doing it using MATLAB. In the command window, you can just type some variable equals transfer function of, and then you can type this transfer function. So what am I doing here? Here I am typing all the coefficients one by one in the numerator, comma, denominator should have all the coefficients as well. Please be careful here. Here it is x cube term plus s square term plus s term plus constant term is not there. So the last term here, the denominator should be 0. So I'm just assigning this transfer function to this x. So now my x is displayed as this transfer function, and it is identified as a continuous time transfer function. Now I wish to plot the Bode plot of this transfer function and find its phase margin and gain margin. Phase margin more importantly. Let us recollect that for any stable system, the gain margin and phase margin should be positive. So when I type a command like this, margin of x, so the first step is storing this transfer function in a variable named x, and then I am typing the command margin of x. The moment you press enter, a diagram will come, your Bode diagram will come, which has details of gain margin and phase margin as this. So this is the image you will get. Here you could see that gain margin is positive and phase margin is also positive. Now comes the most important part. For a good system, that is for a well-designed system or a system to be stable in a good way, your phase margin should lie between 60 degree and 45 degree. This is the golden rule for having a stable system. What if it is greater than 60 degree? No problem. It can go up to 70 degree, 75 degree, something like that. What if it is less than 45 degree? Still, it's not very serious until it goes maybe up to 35 degree, 32 degree, something. So the advised range for this phase margin is to be in this range. In my case, for my buck converter, I got phase margin to be 67 degree, which is okay, which is somewhat in accordance with this. That means, what are we doing here? Let me summarize what we have done here. I have written my Arduino program, and I have found that instead of taking 50 microsecond for the loop function to run once, it is taking 100 microseconds. That is, in my output voltage waveform, if this is my output voltage waveform of my buck converter, instead of taking sample at every 50th microsecond, I am taking sample at every 100th microsecond. Even if this happens, even if I'm taking a sample at every 100th microsecond only, still my system is stable. This is the conclusion here. This is what we are concluding by this process. By checking the closed loop system stability, we are commenting that even if I am doing this, this particular buck converter which I have designed is stable. Right. Now what if it's not? Now what if it's not stable? Assume that you are doing an ideal analysis. You have designed your converter to work properly if it is sampled at every 50th microsecond only. And if there is some additional delay involved, just like which happened here, and due to this additional delay, if your phase margin is going negative, if your phase margin is going to minus 21 degree or minus 15 degree or minus 7 degree, something like this, if your phase margin goes negative, then it means that your system is unstable. So what you have to do is you have to do something to make this phase margin positive and make your closed loop system stable. But how to do that? We are going to see how to do that. So what we did previously is we had a system which had an effect of delay incorporated in it, and this had some value, maybe 57.6. My Ki was somewhere 57.6. Now if I put this Ki, I am getting a transfer function, so my loop transfer function, loop gain transfer function has 57.6 in it, and so I'm multiplying this term multiplied by this term and this term together, and then I'm deriving a transfer function and I'm checking the stability for that transfer function. Now what I'm suggesting you to do is you take, can you do anything with this delay? No, Arduino takes 100 microseconds to run once. If you can do anything about it, well and good. If you are not able to do anything with that, then this TD is out of your control. It is going to stay at 100 microseconds only. This TD is out of your control. So what you can do now is you club this and this together as your plant. You take this effect of loop delay, incorporate it with your plant transfer function, multiply them together and form a new transfer function. Now that is going to be the transfer function of your interest, which you are going to tune again, for which you are going to tune the controller again. So now my plant transfer function will become del V naught of S by del D of S multiplied by 1 minus S into TD, because this is nothing but 1 minus S into TD, and this will be my plant transfer function now. And then I am going to have an integral controller I of S in my MATLAB, and just like we did in the second episode of this entire series, we are going to give a reference signal, produce an error, and then instead of having just del V naught of S by del D of S, we are going to have the effect of delay also. And now we are going to tune this controller using PID tuner app, using the auto tuning facility provided by MATLAB. Now tune this. Now your integral controller will no longer be at 57.6. Since you are tuning with respect to this whole transfer function now, it will come to maybe some other value, definitely not 57.6. Let us assume that it is going to 68.7. Now you take this value and then do this process again, do the above process again. This is your new Ki value, so you will form del V naught of S by del D of S here, and your K will be 68.7 upon S, and then you have a delay block 1 minus S into 0.0001. This is a delay block, and now your loop gain will be the product of all these three. It will be the product of all these three. Now you again form a transfer function with all these transfer functions multiplied. This is going to remain the same in all the case. Now this alone has changed. Now you get a new transfer function. Get the new transfer function. That will be again a loop transfer function, loop gain transfer function. Put that transfer function in MATLAB just like we did before and do the process. So simply what I mean to say is, once you find out the new Ka value, taking the effect of loop delay into account, go back here, do this process again. Go back here, do this process again. Just the difference is, earlier this was 57.6, now this thing will be 68.7. You take this and do all these process again. From here to here, you do this again. Now do the margin of x again, and then see what is your phase margin. It should be positive. It should become positive. It will become positive because you have tuned your controller such a way that you have taken the loop delay effect into account and found a new transfer function, which is the multiplication of loop delay factor along with your planned transfer function. And you have tuned your controller for that. So when you check the stability of it again, it will become positive. It will become some positive value. So again, you can fine tune it to make it fall in between this range, or slightly plus or minus is fine. So this is how you analyze the effect of your closed loop system when you are dealing with a digital controller. After doing all of this, we are going back to the Arduino program, and then we are going to focus on this guy here. So what is the expansion of this particular term? I have already told before, this term is nothing but Ki into Ts into 1 by 2, because this whole term is K into Ts into E plus E previous, the average of E plus E previous. That's the story here. But since E plus E previous is already there, we are going to focus only on this. Now here you will have to plug in the new value of Ki you got, and this Ts should be 100 microsecond. That is, the value of Ts should be, earlier it would have been 0.0005. It would have been 50 microsecond, but now it should be 100 microsecond. Please change these values. Now your difference equation is perfect. It is adjusted for computing the area of the rectangle properly. When I mean to say area of the rectangle, if you have seen my video already, the area of this rectangle is average of these two multiplied by this width, right? And this is two consecutive samples, and we have now found that for two consecutive samples, that is for two consecutive analog reads to happen, the time taken in between these two is 100 microsecond. That's right. But if you are holding 50 microsecond here, then it's not so meaningful. That is why we are changing this into 100 microsecond. So only the sampling time here is 100 microsecond. Your converter still functions for switching period of 50 microsecond. That is not going to change. So when your converter is operating for 50 microsecond time duration, your output voltage will be rising, falling, slightly rising, falling. It will be like this with the average value of 12 volt, right? And each of these rise and fall is, that is, each switching period is 50 microsecond apart. However, you are taking sample at every 100 microsecond. That means first sample may be somewhere happening here. It will leave a cycle, take the next sample here. It may leave a cycle, take the next sample here. and so on. So it goes on like that. So with this, the entire story of implementing digital controller for DC-DC converter gets over. This holds good for almost any DC-DC converter. The principle is same. And if you are going for some other processors other than Arduino, then maybe your switching frequency is high. Even then, all these concepts will still hold good, regardless of what microcontroller you are using. Maybe just the way the program is written or stuff like that will change, but the core concept of what we have seen over the past 13 videos will remain the same. So if you have any doubts regarding this, you can ping me in the comment section. If it's possible, I'll go through it and try to clarify those doubts in the comments as well.